Rainbows, those ephemeral arcs of color painting the sky after a rain shower, have captivated humanity for millennia. These natural wonders appear as if by magic, transforming the sky into a canvas of vibrant hues. From the earliest civilizations to modern times, rainbows have been a source of inspiration and awe. Cultures worldwide have woven myths and legends around these celestial displays. In many traditions, rainbows are seen as bridges to the divine, pathways to other realms, or symbols of peace and unity. They appear in folklore, art, and literature, each culture adding its unique interpretation to this universal phenomenon. A symbol of hope, promise, and even divine favor, the rainbow holds a unique place in our collective imagination. It often appears after a storm, symbolizing the end of turmoil and the beginning of calm. This duality of beauty and hope makes the rainbow a powerful emblem in human culture. But have you ever stopped to wonder what scientific principles underpin this breathtaking spectacle? The rainbow is not just a pretty sight, it is a complex interplay of light and water droplets, a natural demonstration of the principles of optics. Rainbows are not merely optical illusions but intricate displays of physics in action. When sunlight encounters raindrops in the atmosphere, it is refracted or bent, and then reflected inside the droplet before being refracted again as it exits. This process separates the light into its constituent colors, creating the spectrum we see. Understanding the science behind rainbows enhances our appreciation for their beauty. Knowing the mechanics of light refraction and reflection adds a layer of depth to our experience, transforming a simple observation into a moment of intellectual curiosity and wonder. It transforms a fleeting moment of awe into a deeper understanding of the natural world. Each rainbow becomes a reminder of the intricate and beautiful laws that govern our universe, a testament to the wonders of nature and science. So let's embark on a journey to demystify the science behind rainbows. By exploring the principles of light and water, we can uncover the secrets of this natural marvel and deepen our connection to the world around us. To understand rainbows, we must first delve into the fascinating world of light and its properties. Light is an essential part of our daily lives, yet its behavior can be quite complex and intriguing. One of the most captivating interactions of light is with water droplets. These tiny droplets act as miniature prisms, bending and splitting the light into its various colors. Light, which we typically perceive as white, is actually composed of a spectrum of colors. This spectrum includes all the colors of the rainbow, from red to violet. Each color within this spectrum travels at a slightly different speed when passing through a medium. This variation in speed is what causes the light to spread out and form a spectrum. When light passes from one medium to another, such as from air to water, it changes direction. This change in direction is due to the difference in the speed of light in the two media. This bending of light is known as refraction. Refraction is a fundamental concept in optics, and is responsible for many fascinating phenomena, including the formation of rainbows. Imagine a ray of sunlight entering a raindrop. As it enters the denser water, the light is refracted or bent at the surface of the droplet. This initial refraction separates the white light into its constituent colors, much like a prism does. Each color bends at a slightly different angle, creating a spectrum. Inside the raindrop, the light reflects off the back surface. This reflection further enhances the separation of colors. The light then reflects off the back of the raindrop, bouncing back towards the front. This reflection is crucial in the formation of the rainbow. As the light exits the raindrop back into the air, it undergoes another refraction. This final bending of light further separates the colors, creating the beautiful spectrum we see in a rainbow. Why do we see rainbows as arcs rather than straight lines? The curved shape arises from the specific angle at which refracted sunlight reaches our eyes. This angle, approximately 42 degrees, is consistent for each color. Imagine yourself facing a curtain of raindrops. Only the raindrops positioned at the precise angle relative to the sun and your eyes will contribute to the rainbow you see. These raindrops form a circular arc in the sky. We usually only see a portion of this arc. The complete circle is visible only from high vantage points, like an airplane. The separation of colors within a raindrop is crucial to understanding the rainbow's sequence. Remember how each color refracts at a slightly different angle? Red light, with its longer wavelength, bends less than violet light. This difference in bending angles causes the colors to fan out in a specific order. When you see a rainbow, red always appears at the top of the arc, followed by orange, yellow, green, blue, indigo, and lastly violet at the bottom. This arrangement, often remembered by the acronym ROIG-BIV, is a direct result of the varying degrees to which each color bends as it travels through the water droplet. A raindrop's perspective, reflecting and refracting sunlight. Let's shift our perspective and imagine ourselves as a single raindrop suspended in the air after a rain shower. Sunlight streams towards us, a blend of all colors. As the light enters, it bends, separating into its individual wavelengths. We reflect some of this light back, acting like a tiny mirror. A portion of the light continues through us, exiting the other side. As it exits, it bends again, further separating the colors. We, the raindrop, have played a crucial role in creating this spectacle of color. Multiply this effect by millions of raindrops, and you get the grandeur of a rainbow. Polarization, enhancing the rainbow's vibrancy. Polarization adds another layer of complexity to the already fascinating phenomenon of rainbows. Light waves vibrate in various directions. When light reflects off a surface like the back of a raindrop, it can become polarized. This means the light waves vibrate primarily in a single plane. Polarized light affects how we perceive the rainbow. It enhances the colors, making them appear more vivid. The next time you find yourself marveling at a rainbow, remember that polarization plays a key role in intensifying its brilliance. Darker skies above, the shadow cast by a rainbow's brilliance. Have you ever noticed that the sky often appears darker above a rainbow? This phenomenon is not a trick of the light, but a direct consequence of how rainbows form. Remember the specific 42-degree angle required for the rainbow's colors to reach our eyes? Raindrops positioned above this critical angle reflect light away from us, not toward us. This absence of reflected light creates a darker appearance in the sky above the rainbow. The contrast between the bright arc and the darker sky further accentuates the rainbow's visual impact. Beyond the single rainbow, double rainbows, and supernumerary arcs, rainbows, however, are not limited to single arcs. Sometimes we are treated to the breathtaking sight of a double rainbow. Double rainbows occur when sunlight reflects twice within raindrops. The second reflection creates a fainter, secondary rainbow above the primary one. Interestingly, the color order in the secondary rainbow is reversed, with violet at the top and red at the bottom. We might also observe faint, extra bands of color within the primary rainbow, known as supernumerary rainbows. These result from the interference of light waves, a fascinating demonstration of light's wave-like nature. From Aristotle to atmospheric optics, rainbows in science and history. The study of rainbows has a rich history dating back to ancient Greece. These colorful arcs in the sky have fascinated humans for millennia, inspiring both myth and scientific inquiry. Aristotle, the renowned philosopher, was among the first to offer a scientific explanation for rainbows. He proposed that rainbows were caused by the reflection and refraction of sunlight in raindrops, a groundbreaking idea for his time. He correctly attributed their formation to the reflection of sunlight by raindrops. This early understanding laid the foundation for future scientific exploration. Centuries later, French philosopher and mathematician René Descartes further refined our understanding of rainbows. Descartes' work in the 17th century brought a more precise mathematical approach to the study of light and optics. He accurately calculated the angle of rainbow formation, determining that the primary rainbow forms at an angle of 42 degrees relative to the direction of the incoming sunlight. Today, the field of atmospheric optics continues to explore the intricacies of rainbows and other optical phenomena. Modern scientists use advanced technology to study how light interacts with water droplets and other particles in the atmosphere. From the simple act of light bending through water droplets to the complex interplay of reflection, refraction, and polarization, rainbows offer a glimpse into the elegant laws governing our universe. These natural wonders continue to captivate and inspire, reminding us of the beauty and complexity of the world around us.